Hi, my name is Shun, and today my team will be sharing with you the methods and achievements of our group project on topic D, gender classification for CZ4042, neural network and deep learning. My team comprises of Kai-en, Luke, and myself, Shun. We will be sharing with you the following contents. I will begin with sharing introduction, overview, pre-processing, and selection of models, while Luke will continue with data augmentation and pre-training. Lastly, Kylan will finish with the presentation with hyperparameter tuning, evaluation of agents, and future implementations. To begin, we chose gender classification because it piqued our interest. In recent years, there have been rapid advances in artificial intelligence, especially with COVID-19. Facial recognition was used to capture a person's feature for attendance tracking. With similar concepts like gender classification, our goal for this project is to classify genders of faces in an image and design a suitable convolutional neural network to achieve this goal. Next, I will be sharing a flowchart for better understanding of our project. Firstly, we will perform data preprocessing. As the given gender labels are male and female, we have converted them into binary for our computation. We also ensured to form data directory and label as attributes before training them with three different models using suitable hyperparameters. After the model with highest accuracy is selected, we perform pre-training and data augmentation. More details of the types of augmentation and results will be shared by Luke later. The pre-trained weights from slab A will then be loaded to perform inferences on an Adian's dataset before we perform hyperparameter tuning in a specific order which will be shared in detail by Kayan later. Lastly, we will evaluate the results and share with you the factors contributing to the best accuracy for our model. For pre-processing, the slab A dataset with over 200,000 images was used for pre-training the model, whereas hyperparameter tuning is done on Adian's aligned dataset because the photos in aligned dataset have been pre-processed using frontalization that will help to improve performance of facial recognition systems. In Adian's dataset, the male and female labels are converted into 1 and zeros, respectively. After removing the incorrect labels, we are left with approximately 12,000 images for gender classification. The image directory is created using the user ID and original image file. These two attributes are then placed in the data frame. Train test split of 80 to 20 is conducted on Adian's dataset, where the RGB coefficients of the images are divided by 255 to rescale its value to in between 0 and 1 to ensure that the inputs are normalized before feeding into the neural network. Before we talk about the selection of models, here are the parameters used for training the base models for comparison in the initial phase before hyperparameter tuning. Do note that Adam Optimizer is used for EfficientNet and ResNet50, whereas SGD Optimizer is used for Levi-Hessner. As specified in the Levi-Hessner's paper, we have made a faithful reconstruction of their CNN. However, upon training with a validation set, it can be seen that the validation accuracy does not improve and stops at 0.47. Hence, we have modified the CNN by changing the activation function to sigmoid to tackle binary classification problem, as Levi-Hessner may have gone with softmax as their activation function to consider both age and gender, making it a multi-class classification problem. ResNet50 is a convolutional neural network with 50 layers that serves as the foundation for many computer vision applications. It has also won the ImageNet Large-Scale Visual Recognition Challenge in 2015. Thus, it was chosen as a potential architecture. EfficientNet is a CNN architecture and scaling method that uniformly scales all dimensions of depth, width, and resolution using a compound coefficient. It was considered as one of the potential architectures as it transfers well and achieves state-of-the-art accuracy on many transfer learning datasets. The validation accuracy peaks the highest at 0.8688, with validation loss at its minimum at 0.5153 amongst the other three architectures. Hence, EfficientNet was chosen. Now, I will pass my time to Luke.
Data augmentation is a technique used to artificially create new training data from existing training data. This is done by applying domain-specific techniques to examples from the training data to create new and different training examples. It can potentially help us increase the size of the dataset and introduce variability so that the dataset can generalize better against unseen test set. It will also help the model to not overfit. Since Adian's is a smaller dataset with less than 8,000 training data after train test split, we decided to apply data augmentation techniques to it before we proceed with the hyperparameter tuning. Here are the data augmentation techniques that we attempt to apply to our dataset. This includes vertical and horizontal flipping, rotation, as well as changing the brightness and saturation of the images. Without augmentation, the original validation accuracy is at 0.8668. We added the augmentation one by one, starting with horizontal and vertical flipping. It has shown to improve the validation accuracy to 0.8765 at convergence. Hence, we will include this augmentation in the rest of our testings. When paired with rotation, contrast, and brightness, however, the accuracy went down. Hence, this shows that horizontal and vertical flipping is the only useful and viable augmentation for this model and dataset. For optimal performance in a short amount of time, we pre-train the model on another large dataset, CZ4042. The weights are then saved to be used later on when tuning the hyperparameters on the Adient's dataset. Since CZ4042 dataset is similar to Adient's dataset, it can definitely help to improve the accuracy of the training on the Adient's dataset. In this slide, we can see that the pre-training on CZ4042, which is the much bigger dataset, accuracies has gone up to 0.99. Hence, it shows that it will definitely help with the subsequent training and tuning on the Adient's dataset. Thank you for paying attention. For the next portion, Kyan will take you through hyperparameter testing on the Adient's dataset.
With regards to hyperparameter tuning, we had to decide on an order to tune the parameters as the model performance is reliant and affected to different degrees by different parameters. This is the order that we have chosen. We will first tune the learning rate, followed by batch size, number of hidden layers, and finally the number of neurons in those hidden layers. Rationale for this order is that learning rate causes the biggest variance in test set performance, followed by batch size, and then the design of the neural network. We have found this order based on the research article referenced in our report. The learning rates that we chose are 0.1, 0.001, and 0.001. Learning rate controls the adjustments of weights of the network with respect to loss gradient, and from this table of results, it can be seen that with a higher learning rate of 0.1, it yields the best result as validation accuracy at conversions is the highest at 0.89. Next, for batch size, we have chosen the three batch sizes of 50, 64, and 128. After our tests, we observed that validation accuracy is the lowest at batch size 128, while it has the highest value at batch size 64. Thus, we will be continuing the rest of the experiment with batch size 64. Then, for the number of hidden layers, we have set it to 3 layers as it yields the highest validation accuracy at convergence. Because there are 3 hidden layers, we will also add 3 dropout layers to each of the outputs of these 3 hidden layers. Lastly, the number of neurons in the hidden layers are chosen to be 64 due to the highest validation accuracy at convergence. Using this tuned hyperparameters and model, we ran an evaluation on the Adient's dataset and managed to come up with a test accuracy of 0.89 and test loss of 0.3. Compared to the validation accuracy after updating the number of neuron layers, the test accuracy is slightly lower. However, given that the test accuracy is still pretty high, it shows that the model did not overfit and could generalize well against unseen data. Therefore, it shows that the process of data augmentation, hyperparameter tuning, and pre-training is effective in increasing the accuracy of the model. Despite the success we have found in our model, there are still future considerations regarding our work due to certain limitations encountered throughout the course of this project. First and foremost, the biggest limitation we faced were the time constraints. Given the limited time we had for the assignment and that the time taken for each epoch, in particular the first one, is quite long, we decided to scale down the testing and tuning. In actuality, there are even more values to be tested. Consequently, we weren't able to do further exploration in other areas like weight decay or batch normalization that could help prevent overfitting of our model. We would also have liked to tackle the aspect of age consideration to do gender classification by using the gender-specific age characteristics and age-specific gender characteristic inherent to these images. With that, I would like to conclude our presentation. Thank you.